Okay, first of all, I want to express my profound gratitude for the organizer for the invitation. It's my great honor to give a talk in this conference. Today, my topic is on conformal restriction. My talk will be divided into 4 parts. First, I will give an introduction to Brownian section exponent and conformal restriction. The second and the third part is idea of the proof for the main result. And in the fourth part, I will talk about some related properties. So first, a Brownian section exponent. So suppose we have 2 independent Brownian motion. Their starting distance is 1. And then we run both of the Brownian motion after time t, and we want to calculate what's the probability that the 2 paths avoid each other. And then we can guess that this probability will decay like a power law of t. And we define this C11 as this power. So this C11 is called the intersection exponent between 2 independent Brownian motions. We can generalize this. This is one simulation of 2 independent Brownian motion, and restrict it to they avoid each other. And then we can generalize this exponent a little bit. So now we consider we have 2 packets of Brownian motion. The first packet has n Brownian motion. The second packet has n Brownian motion. And we run all the Brownian motion after time t. And we want to calculate what's the probability that the 2 packets avoid each other. And again, this probability will also decay like a power law of t. And we define Cnm as this power. And we can further generalize this intersection exponent. So now we consider we have p packets. The first packet has n1 Brownian motion. The second packet has n2 Brownian motion. And the last packet has np Brownian motion. We run all the Brownian motion after time t, and then calculate the probability that all of them avoid each other. All these p packets avoid each other. And again, this probability will also decay like a power law of t. Yes?
In which dimension the Brownian motion?
2-dimensional. Everything is in plane. So this is, see, N1 to NP is called whole plane Brownian intersection exponent. And now we just put a little restriction to this whole plane case. So now we consider Brownian motion, but we require all the Brownian motion to stay in the upper half plane. And we still calculate the probability that all packets avoid each other, but we also require all Brownian motion to stay in the upper half plane. So here the distance between 2 packets is still 1. And the distance from the real line is also 1. So this probability is still decay like a power law of t, and we define this power as c tilde. Here we can see that because we require our Brownian motion to stay in the upper half plane, so of course the second probability will be much smaller than the first one. So this tells us this exponent should be much bigger than the previous one. And this exponent is what we call a half-plane intersection exponent. So then the question is, what's these 2 exponents? In fact, the explicit formula for these 2 exponents is already known. So the first one is the whole plane intersection exponent. The second one is the half-plane intersection exponents. These formulas are conjectured by physicists in 1988, and later they're proved by mathematicians in 2000. The proof of these 2 formulas involve SLE calculations, but I won't talk about the proof of these 2 formulas. The topic I want to talk about is, in the proof of these 2 formulas, a first important step is the observation that some conformal invariant random measure with certain restriction property are identical. This is my topic. It's called conformal restriction. So now I have introduced 2 intersection exponents, and next I will introduce what is conformal restriction. So for this conformal restriction, we first start with an example. This example is the Brownian excursion in the upper half plane. So suppose this is upper half plane. Here is the origin. Here is infinity. A Brownian excursion in the upper half plane is just, roughly speaking, it's just a Brownian motion in the upper half plane from the origin to infinity, but it doesn't touch the other boundary points. This is a Brownian excursion. For this Brownian excursion, it has 2 important properties. The first property is called scaling invariance. So suppose E is a Brownian excursion. Lambda is a constant, positive constant. Then the scaled Brownian motion, the scaled Brownian excursion lambda times E has the same law as a Brownian excursion. So this is called scaling invariance. The second important property is called restriction property. Here, it means if we fix the deterministic set A here, we condition on this Brownian excursion to avoid this set A. Then this conditional measure of this Brownian excursion is just it has the same law as the Brownian excursion in the remaining region. Or in other words, we can also put it in this way. So suppose we fix a subset A. We define a conformal map phi A. It is from H minus A onto the upper half one and fix the origin at infinity. And then the image of this excursion under this conformal map has exactly the same law as the Brownian excursion in the upper half one. So condition on this event, phi A E has the same law as itself. This is called the restriction property of Brownian excursion. And our motivation for conformal restriction just from here. So we want to define a random measure that satisfies both scaling invariance and restriction measure. And first of all, we know that at least the Brownian excursion satisfies such a property. And our next question is, what's other random measure with these two properties? So before going on, I also want to mention one quantity about this Brownian excursion. So suppose K is the filling of our Brownian excursion. So it's just that we take the left boundary and the right boundary of the Brownian excursion and fill everything inside. And now it's become a closed set. So suppose K is the filling of a Brownian excursion. The probability of K avoid A is phi A prime 0. So this phi A is the unique conformal map from H minus A onto the upper half one. Fixed origin, fixed infinity, and is normalized at the infinity. And we can explicitly calculate what's the probability that this excursion avoid a fixed set A. And now we can introduce what is a conformal restriction measure. The idea just starts from here. So we define a conformal restriction. We say that a random set K satisfies Chordal conformal restriction property if it has the following two properties. First, it is scale invariance. So for any constant lambda times K has the same law as itself. Second, it satisfies restriction property. For any fixed set A, condition on the set of weight A, phi AK has the same law as itself. So of course, we already know that Brownian excursion has these properties. And of course, the union of any independent Brownian excursion also have these properties. And if K is the union of any independent Brownian excursions, we can also calculate the probability that this K avoid A. So it's just the probability of 1 to the power n. Okay, so this is the definition of Chordal conformal restriction property. And then our question is, so what is the whole family that random set satisfies Chordal conformal restriction property? The answer is here. So a Chordal conformal restriction measure is fully characterized by a positive real beta. And this beta is related to this random set in this way. So for any set A, the probability of K avoid A it is phi A prime 0 to the power beta. And the second part is called existence. So this measure exists if and only if beta is big enough. So there is a lower bound for this beta, and this lower bound is 5/8. And we already know that if K is the union of any independent Brownian excursions, it satisfies this relation. And the exponent here is n. So here we can also get a sense that, in fact, for this measure, this beta corresponds to how many Brownian excursions we have in this set. But now this beta is it doesn't just take values in integer numbers. It can be positive reals. And here we can also have a sense that for this beta, if the beta gets bigger, our random set becomes fatter. Okay, so this is the Chordal conformal restriction property. And then the counterpart question for this one is the radial case. So in the chordal case, why I call it is chordal? Because this random set also always contains two boundary points. So infinity and origin. And the radial counterpart means we require this random set to contain one boundary point and one interior point. So this is the radial counterpart case. So for the radial case, we define a random set satisfies radial conformal restriction property if it satisfies this relation. So first, it contains the boundary. So now suppose we are working in the unit disk. So this random set contains the boundary point 1 and also contain the interior point origin. And we say that it satisfies radial conformal restriction property if for any set A, the condition on K avoid A, it has the same law. After this conformal map phi A, it has the same law as itself. And now this phi A is just from U minus A onto the unit disk, fixed origin and that boundary point 1. So this is the radial counterpart for the conformal restriction property. And the question is, what is all the family of this random set that satisfies radial conformal restriction property? And the conclusion is this. So the first part, a radial conformal restriction measure is fully characterized by a pair of real numbers, alpha and beta. And these two reals are related to this random set in this way. So the probability of K avoid A equals the product of two things. This part, phi A prime 1 is, so 1 now is the boundary point to the power beta. So it has the same row as in the Chordal case. But now we have one more quantity here. Phi A prime at the origin to the power alpha. So this is the relation between these two real numbers to this random set. Here, this beta is, I would call it boundary exponent. Alpha is the interior exponent. So this is the first part, characterization. The second part, existence. So this measure, alpha beta exists if and only if there's a lower bound for beta and there's an upper bound for alpha. So first, why the bound for alpha is the upper bound? So a little different from the Chordal cases. Now our phi A is the unit is from unit disk minus A onto the unit disk. Normalize the origin and this boundary point. For this conformal map, it is unique. And for this conformal map, we know that the derivative at 1 is always less than 1. But the derivative at the origin is always greater than 1. So, of course, it is impossible to have all combination of the right-hand side here, because if alpha is very large, beta is very small, then the right-hand side will be greater than 1, which can't be a probability. So, of course, we should have some restriction on alpha. So this tells us why we have the upper bound for alpha. So alpha can't be too large. If it is very large, the right-hand side will be greater than 1. Okay, so this is the full characterization of radial conformal restriction measure. And in my talk, I will talk about the idea of the proof of these two main results. Before I talk about the proof of the idea of the proof, let us see why there is difference between Chordal and the radial case. Because we can see that in the Chordal case, we only have one parameter, but in the radial case, we have two parameters. Why this is that different? So the reason is, in the Chordal case, when we define conformal restriction measure, we require this measure satisfies two properties. The first is conformal invariance. Second is the restriction property. And finally, we can prove that there exists only one degree of freedom. But when we introduce radial conformal restriction property, there is no counterpart for scaling invariance. We only require this restriction property. So now we have one less restriction, and the answer will have one more degree of freedom. So this is the reason why there is only one parameter for the Chordal case, but two parameters in the radial case. Okay, so this is the introduction part. I introduced a Brownian intersection exponent, and introduced the conformal restriction property and our main results. So in the second and the third part, I will talk about the idea of the proof. In the fourth part, I will show you how these two concepts are related to each other. So first, we talk about the proof of the characterization part. So this is the Chordal case. In the Chordal case, the characterization part of the statement says, a Chordal conformal restriction measure is fully characterized by one positive real number, beta. And the beta is related to this random set in this way. So first of all, if we have a random set K, and it satisfies this relation, we can easily check that it does satisfy scaling invariance and restriction property. So the only question is, why there's only 1 degree of freedom? And the idea of the proof is, the first step, we want to calculate what's the probability that this random set hit a small ball on the boundary. So now we are in the upper half plane. This is our random set K, and we draw a small ball on the boundary. We want to calculate what's the probability that this random set hits this small ball. So of course, this probability will be very small when the epsilon is very small. In fact, we can derive that this probability is decay like an epsilon squared. Just from the restriction property itself, we can derive that this measure will decay like epsilon squared. And now what we do is we normalize this probability by epsilon squared and let epsilon goes to 0. This will give us a limit, lambda x, and this lambda x is a function in x. And next, by scaling invariance, we have a nice property for this lambda x, because now, since we know that this random set K is a scaling invariant, so if we calculate the probability that it avoids a small ball, the center is xy, so both xy are positive reals. So the probability of this set hit this small board. Since K is scaling invariance, we know that this probability is the same as we scale everything by y. And from the definition, we know that this will decay like lambda x times epsilon squared over y squared. But from the original definition, we also know that this will decay like lambda xy times the epsilon squared. So this tells us lambda xy is lambda x over y squared. So this equation fully characterizes this function. And we know that this function should have this form, so there's only one constant c0 there. And in fact, this c0 corresponds exactly to this exponent beta. So this explains why, for the Chordal conformal restriction, we have only 1 degree of freedom. Okay, so this is the Chordal case. And next, for the radial case, the conclusion is a radial conformal restriction measure is fully characterized by a pair of reals, alpha and beta. So it's the same as before. If we have a random set K satisfy this relation, we can check that it does satisfy restriction property. So the question is, why there are only 2 degrees of freedom? The first step is the same as before. Now we are in the unidisc. This is the random set K. We draw a small ball on the boundary. We calculate what's the probability that this set K to hit this small ball. Again, this probability will decay like epsilon squared. We normalize this probability, take the limit, and it will give a function lambda x. And now the second step will be different, because in the radial case, we don't have scaling invariance anymore. So we have to find something to replace scaling invariance to analyze this function lambda. So what we use here is called commutation relation. So now we draw 2 small balls on the boundary. Bx epsilon and by delta. We calculate the probability that this K avoid both of them. Hit both of them. And of course, we know that this probability will decay like epsilon squared times delta squared. So we normalize this probability by epsilon squared and delta squared. And now we want to take limit of the epsilon. We want to let epsilon and delta goes to 0. But now the trick is, so we have 2 small quantities epsilon and delta. When we let them goes to 0, we can choose the order. So first, we can choose first let epsilon goes to 0 and then let delta goes to 0. And this limit will give the left-hand side here. And then we switch the order of the limit. So we first let delta go to 0 and then let epsilon goes to 0. The limit will become the right-hand side. And then we check that we are allowed to exchange the order. So after we exchange the order, the limit should be the same. And this tells us the left-hand side equals the right-hand side. So in this commutation relation here, this big F and the big J are explicit function in xy. So this commutation relation will replace the scaling invariance as in the Chordal case. And then we solve this equation. It will give us solution lambda x in this form. And here we say that there are two constants, C0 and C2. And this tells us why there are 2 degrees of freedom in the radial case. Okay, so this is the proof of the characterization part. And then I will go to the idea of the proof of the existence part. For this existence part, inevitably, I should introduce what is an SLE curve. So I will start with what is an SLE curve. An SLE curve is a random fractal curve in simply connected domain from one boundary point to another boundary point. It is introduced by Odette Schramm as the candidate for the scaling limit of discrete models. And it is a random curve with the following 2 properties. First property, conformal invariance. So suppose we have a curve in D from A to B. Phi is a conformal map. Then the image of this curve should have the same law as an SLE curve in phi D from phi A to phi B. This is conformal invariance. Second, domain map property. Suppose we have a curve in D from A to B. Given the first part of this curve, the future part of the curve should have the same law as an SLE curve in the remaining region, starting from this tip to the endpoint. This is called domain map property. Here I have 2 remarks for these 2 properties. The first remark is, these 2 properties are natural property from discrete models. So suppose we have a region D. We have a discrete lattice inside this D. Let us take the simplest example, this critical population. So at each vertex, we have black or white with equal probability 1/2. And we require all boundary points to be white here, all boundary points to be black here. And then for the interior site, it is black or white with equal probability 1/2. This is the critical population model. For this model, we know that there exists a unique interface starting from A and at B, such that it separates black and white vertices. This is called the interface for critical population. For this critical population, we can see that if we follow this interface, stop at some point, and then the future part of this curve is again has the same law as an interface for critical population in the remaining region. So this is a discrete version of domain map property. And for SLE, when we introduce it, we want to study the scaling limit of discrete models. So if the scaling limit exists, the scaling limit should also satisfy this domain map property. So that's why we introduce the random curves with these 2 properties, because they are natural from the discrete models. The second remark is, in fact, a random curve satisfies both these 2 properties. The combination of these 2 properties is very strong. Suppose we have a curve that satisfies both these 2 properties. So we run this curve up to a small time epsilon. We define phi 1 as the conformal map from the remaining region onto the initial region. Set the tip to the starting point and fix the end point. Then the image of the future part of the curve should have the same law as an SLE curve in D from A to B because of the conformal invariance and domain map property. So this tells us the image of this future part under this conformal map is independent about what happens in the first step. And it has the same law as an SLE curve in D from A to B. So now we can repeat the same procedure. We run the curve up to a small time epsilon, define phi 2 as the conformal map from the remaining region, and send the tip to the starting point and fix the endpoint. And again, the future part of the curve will also have this, under this conformal map, will also have the same law as an SLE curve in D from A to B. So this procedure tells us if a curve satisfies both conformal invariance and domain macro property, in fact, we can just reconstruct this curve by concatenating all IID small slits. So this tells us if a curve satisfies both these two properties, there's not so much choice for the curve because the law of the first small piece will determine the law of the whole curve. So this explains why, in fact, there is only one parameter of family satisfies this conformal invariance and domain macro property because there's not so much choice for them. And this one parameter family is called SLE kappa. It is indexed by a positive kappa. For kappa between 0 and 4, that corresponds to the simple curve, and this is the case I will focus in my topic. As I said before, SLE curves are introduced as a candidate for the scaling limit of discrete models. Since their introduction, they have been already proved to be the scaling limit of several discrete models. For example, SLE2 corresponds to the scaling limit of loop erased random walk. SLE3 corresponds to the scaling limit of the interfacing critical Ising model. SLE4 is the scaling limit of the level line of discrete Gaussian free field. And today, I will focus on SLE asserts. So first, a conjecture about SLE asserts is that it is conjectured to be the scaling limit of self-avoiding random walk, but it's still open. Second, there's something already known about SLE asserts is that the frontier of a Brownian excursion is locally an SLE asserts. So suppose we have a Brownian motion. If we just look at the right boundary of this Brownian excursion, so I call it the frontier of Brownian motion, this frontier is locally an SLE asserts. So this is something we already know, and it is the scaling limit of self-avoiding random walk is still open. Okay, so this is the introduction for SLE. And now I want to introduce SLE kappa rho. When we introduce SLE kappa, we can see that it is a simple curve there, and it is symmetric. Because when we introduce there's no left or right, it is symmetric. And for SLE kappa rho, it's just a little more complicated. So from the left-hand side, when rho is negative, it corresponds to we have a attraction from the left-hand side. So now the curve will be put a little to the left. And when rho is positive, it corresponds to we have a repulsion from the left. And now this curve will be put a little to the right. So it's not difficult. So we have one more parameter. Rho is just corresponds to this curve is a little to the left or a little to the right. So now it's no longer symmetric. When rho is 0, it's the same as SLE kappa. But when rho is not 0, it is just a little to the left or a little to the right. And now we can talk about the idea of the existence part. For the existence part in the chordal case, so the conclusion says the chordal conformal restriction measure exists if and only if when beta is greater than 5/8. So first of all, by a calculation for chordal SLE asserts, we know that chordal SLE asserts satisfies exactly the conformal restriction property with the exponent beta equals 5/8. Note that this is the lower bound for this beta. And then we can construct what's the measure when beta is greater than 5/8. So the idea is this. When beta is greater than 5/8, we know that this set will look like this. And our idea is we first sample is the right boundary. So when first sample is the right boundary, we can calculate that the right boundary has the law of SLE asserts with rho. This rho is positive, so the right boundary is a little put to the right. And then given the right boundary, the conditional law of the left boundary is SLE asserts with another parameter rho minus 2. And this rho is related to beta in this way. This is the construction for beta is strictly greater than 5/8. And the last step is why it doesn't exist for beta smaller than 5/8. The idea here is simple, because in the first step, we already see that when beta equals 5/8, it is a simple curve. And as I explained before, as beta gets bigger, the set will become fatter. So as beta gets smaller, the set should be thinner. And now when beta equals 5/8, it is already a simple curve, and then it can't be thinner anymore. So this gives us an idea that this is a lower bound, because it can't be thinner then. Okay, so this is the idea of the proof for the existence part of the chordal case. And then the existence of part of the radial case. In fact, there are several different constructions for the existence of the chordal case. I only choose this method because this is exactly the idea we can generalize to the radial case. Okay, then the existence part for the radial case. So the conclusion says the radial conformal restriction measure exists if and only if there's a lower bound for beta and an upper bound for alpha. So the first step, by a calculation for radial SLE acers, it corresponds to a radial restriction measure with beta equals its lower bound, and alpha gets its upper bound in this case. And then for beta strictly greater than 5/8, first we construct a sample when alpha is the upper bound. And the idea is same as the chordal case. In the radial case, but first, the sample is right boundary. It is a radial SLE aces row. Radial SLE aces row. And given its right boundary, the left-hand side is the conditional law of the left-hand side is a chordal SLE aces row minus 2. And we can calculate directly that the obtained random set satisfies the radial restriction measure with boundary exponent beta and alpha exponent equals c beta. This is the upper bound of alpha. And next, for a smaller alpha, so beta is there, but for alpha smaller than its upper bound, how we construct it. So this is, in fact, this is very easy because as long as we have any random set satisfies radial restriction measure, then we put some independent Brownian loop soup around our region with intensity C. So it's an independent Brownian loop soup around our region with intensity C. Then the union of the two will correspond to a restriction measure. The boundary exponent is the same. The interior exponent will become alpha minus C. So as long as we have an alpha, all quantities smaller than alpha can also be constructed by putting an independent Brownian loop soup around our region. This is how we construct a smaller alpha. And the last step is why this radial restriction measure doesn't exist for beta less than 5/8. And in fact, the reason is the same as the chordal case. And the idea of our proof is we push this interior point to the boundary. So now it is the region by the conformal map. We can put this interior point as -1 plus the epsilon, so it becomes here. And we push this radial case, this interior point towards the primary point, and the limit should be the same as a chordal restriction measure. And in the chordal case, we know that beta cannot be smaller than 5/8. So this implies the radial case. In the radial case, the beta also can't be smaller than 5/8. So this is the idea of the proof for the existence part. And now I can go to the last part. So in the last part, I will talk about how Brownian intersection exponents are related to restriction measures. So first of all, consider we have two chordal restriction measures, K1 and K2. If they are just the independent two samples and we take the union of the two, of course the union will become a chordal restriction measure, and the exponent is just a summation of the two. But now we want to do something more. We want to condition that these two sets avoid each other. So of course, and then take the union of the two. And then the union of the two would become the factor by B, then just to put them together. And so now we condition on these two sets with each other. K is the union of the two. Then this K corresponds to the chordal conformal restriction with exponent C tilde, and this C tilde is the half-plane intersection exponent I introduced at the beginning. And then we can generalize this idea. Suppose we have K1 to Kp. They are our chordal conformal restriction samples with different exponents. And we restrict condition on that there is no intersection. Take the union of all of them. Then the union corresponds to chordal conformal restriction sample with C tilde. And this is the half-plane intersection exponent. So this is how they are precisely related between the Brownian intersection exponent and the chordal conformal restriction measure. And we also have the similar property for the radial case. So suppose we have two radial samples, K1 and K2. We condition on there's no intersection, take the union of the two, and then it corresponds to radial restriction measure with the interior exponent, boundary exponent there. So now the boundary exponent is the half-plane intersection exponent, and the interior exponent is the whole plane intersection Brownian intersection exponent. And the same idea for K sets. So K independent one, condition on no intersection, take the union of all of them. The union has the same law as a radial conformal restriction measure. The boundary exponent becomes the half-plane intersection exponent. The interior exponent becomes the whole plane intersection exponent. So this is how Brownian intersection exponent and the conformal restriction measure are precisely related. And next, I will talk about the cut point dimension of this chordal conformal restriction measure. So suppose K is a chordal conformal restriction sample with the exponent beta. Say K is the cut point of K. So what do I mean by cut point? So suppose K is connected. The cut point of K, I mean that if we remove this point from K, then K minus this point becomes disconnected. So this is the cut point of a connected set. And for this random set K, we can see that the intersection of its left boundary and right boundary corresponds to exactly the cut set of this set, the cut point of this set. And we can derive that the cut set has also dimension given by this formula. If you know some formulas in quantum field theory, the KTZ relation, you can tell that this is closely related to this KTZ relation, relating the Hausdorff dimension and the quantum weights. Okay, so the last is, for this chordal conformal restriction, we know that when beta equals 1, it corresponds to Brownian excursion in the upper half plane. So in fact, for the Brownian excursion, we already know that the cut point has dimension 3/4. It is predicted by physicists a long time ago, and it is precisely proved by mathematicians in 2001. And our result is consistent with this already exist results. Okay. Thanks for your attention.
Thanks so much for this very beautiful talk. Are there any questions or not?
Sorry. Can you come back to the characterization part for the radial case? You talked about commutation relation because we don't have the self-similarity argument. Is it right?
Yes.
Thank you. So basically, my question, very naive, sorry, it's out of the done. But the argument you put here, you take two balls and you scale in your, with respect to epsilon going to 0, the impact. You could use that even in in the previous case where you have self-similarity, is it true?
Yeah, it's also true, but in that case, if you use this commutation relation in the chordal case, you will solve an equation and finally you will get 2 degrees of freedom. You can't exclude 1 degree of freedom from that case.
Yes.
Yeah, but in fact, in the chordal case, there is only 1 degree of freedom if you use a scaling invariance. Yeah, exactly. So you can also use the same procedure for the chordal case, and then finally you will also get a 2 degree of freedom. But in fact, this is more than there should be.
So how would you use?
So this also explains why there are 1 degree of freedom in the chordal case, but 2 degree in freedom of the radial case. Because in the chordal case, we have one more restriction. It is the scaling invariance, and that scaling invariance excludes 1 degree of freedom in this case.
So you consider half plane and the circle. Would this be very different for other domains?
So as long as they are conformally invariant, they are the same thing. It's just the disk is easier to describe.
But if you have a non-simply connected domain, if a non-simply connected domain.
For non-simply, because our important tool is Riemann uniform mapping representations, the theorem, yes. So we always use the simply connected equivalent, and there we use conformal invariant and say they should be the same. But if you are not simply connected, we can't use that property.
So what would happen in that case?
I guess, so I also consider what happens if we consider a random set in the annulus, say, and then I guess the degree, there will be much more degrees of freedom. And it's difficult to construct all of them.
But Daplinzan has constructed SLEs, right?
Pardon?
Daplinzan has constructed SLEs for multiply connected domains. He has results. Maybe
Are there any other questions? I have actually a question. So in the chordal case, there is a scaling restriction, and the scaling parameter is 1. And the exponent of the scaling parameter is 1. And could you imagine to have like a scaling parameter of any order? So you have lambda k, which is in distribution that equal to k.
The exponent beta here.
So just in the restriction we impose on the chordal case, you have 2 restrictions. And the first one is the scaling
invariance, yes.
And the scaling is that lambda k is identical in distribution to k.
Yeah.
And could you have a lambda to some power alpha?
Yes, I guess this is maybe this question is very related to self-similarity.
The idea would be to make the connection between the two conformal and Cornell when you relate the scaling parameter.
Yeah, I think this is also an interesting question because when we introduce chordal conformal restriction property, we ask that lambda E has the same law as E itself. But yeah, the next question is what happens if we put an alpha there? Yeah, I think the curve will become more fractal, depends on alpha, and it will correspond to something else. But yeah, this is an interesting question, and I never think about it.
And could it make a link between the two cases? When alpha goes to 0, for instance, will be back?
No, I don't know.
Because in the chordal case, you have 2 restrictions. And the second restriction is the same as in the conformal case. Is that correct?
Yeah. In the radial case, we only have a restriction, but in the chordal case, we also require scaling invariance.
Yeah, it was okay. Thanks so much. Are there any other questions? So let's thank our again.